Okay, so continuing on, this is like part 2 of that homework. I called it problem 1, but there's only one problem where we're trying to figure out the mass moment of inertia of the cis plastic. I just use plastic as a density. Why the hell not? Spaceship, where we know all of this information, and we also know from SolidWorks we're able to find what the mass moment of inertia and all this other stuff is. So what we previously did is we created a table. Using a table, we found the mass right here. Right, if we can get that to focus, yep, 12,631. And we were able to find, by using these distances and getting the total, we could call it mass moment, right? This is like the first mass moment. We could divide that total by the total mass, and we get 1.941. And if we take a look at what I had in here for SolidWorks, let's see. Yeah, I guess I'm going to use this one right here. And if I can get this over to the side, you could see that I got 1.95 compared to my 1.94. But notice also that the mass is slightly different. And the reasoning behind that, let's see, I can get, yeah, I'll just get rid of all that right here. Okay, so what I had done is I found the volume from all of these different parts in a previous, but beforehand, estimated based on cylinders and cones and that kind of thing. What I think I should also do as part of this solution is I should probably also show you doing it in Excel. It's not that difficult to do, but it's you know, this is a life skill. You might not know to do it unless you had seen it, right? So I'm going to make a little table right here, and maybe I will do this and this at the same time. So maybe you can see that. And unfortunately, my keyboard's in the way here, so I can go. So I'm going to go part 1, part 2, part 3, and part 4. And see, the thing with doing in Excel, though, is you might not be able to see all the things that get done. Depends on how you set it up here. So maybe I want to move, I will do this, I'll move the keyboard out over here. And move this down right there. Okay, so my MI, that for the first part was M. We'll just type in the value, and we just type in the value. For this one, we had to have set equals and go 3 times our 535, and then here we had to set equal 3 times our 60. Our, what do we say, 21.9. Cool. And then here we did a 3.66 divided by 2, right? And here we had we had the cone, which is 1.5 divided by 4, but we also had to add in 3.66, and we had 1.83 divided by 2. And then lastly, oh yeah, we also had that once again, right? So if I'm lazy, I'll just go like that. We know it's right there. And now here's the MI times ZI, right? So I'll set that and go boom, that times that. And I can just drag this down, right? So all of them are there. And I can also hit the summation button and get the sum right here, and here I'll do it again. Hit the sum. This is also a pull down, by the way. This is also a pull down for different things, but just where it's shown right there. Sum is the first one. So somewhere over to the side, I'm going to write Z bar is equal, and maybe I should actually move this over just a little bit, like that, and say that we have this is equal to that divided by that. And so here, with a lot more sig figs, is our answer. And it's nice when you have a table to put some borders on it. And we might go M equals maybe right here. And then total. I don't know. There's something like along those lines right there. I don't know. I'll leave that out. But it's nice to put like little extras. And like I like to make a little bar like there sometimes, and like there, just to show, you know, maybe even to center all of these. Sometimes that looks better, right? Okay, so we're also going to do this for our mass moment of inertia, right? So we're going to keep that thing going. So let's go to the next part of this, which is the mass moment of inertia. So we're going to expand that up there. And let's go for the mass moment of inertia. All right, so from our doohickeys, okay, so we want to have the X, Y, and Z, and it's depending on, do we want a really long table or do we want different tables for each of the X and the Y and the Z's? Trying to cram it all in one spot can really just make things bad. So let's go, and I was actually kind of thinking of only having you do it about the Z-axis, and that would be pretty much what you'd want, right? Because that's about the thing spinning right there, you know, like spinning this way, right there, right? But we also might want to know about it flipping in either way, right? And the X and the Y are not the same in this one, so that's a little bit of a and I think actually we're going to have a little bit of a hard time with this piece right there, I suspect. I have to put a little extra thought into it. But most everything in this, with the exception of the cone, is going to be a mass moment of inertia that we would get, if I can find it, centers of gravity and volume, that's not it. We want, oh, I think this is actually in chapter 9. Yeah, it's actually in chapter 9 of, if you have the combined version of the book, to find some of the fundamental pieces and parts, right? There's some extra stuff in here that we don't need. Right, so these are all area moment inertias. We want mass moment inertia. There you go. Okay. So this is in the larger book. Once again, there was a chapter. It was Appendix B of the standalone dynamics book, but it's actually in chapter 9, 9.5, I think. Yeah, 9.5 for the mass moment of inertia in the large combined book. And so we have, here's our fundamental pieces. Here's our cone. But we're mostly made out of these guys right there. But we're going to take them in different axes, right? So down the center, we're going to have, when it's going down the spinning about the long axis, which, well, it doesn't necessarily have to be long, but it's fairly long. It's going to be 1/2 mass times the radius squared, right? But if we do it like a, so that's like this one right there. But if we do it like a baton twirler, right, either way, it's going to be 1/12 mass and then A and then L right there. So we get the L squared. So 3 times that A, which is the radius, and then times L. So, yeah. One of the things we might want to consider when we're doing Excel versus this is it might be better to put those parameters as a thing. So I might not necessarily do it in when I'm approaching it from by hand. But so because we're doing things by Excel and by hand, I'm going to do it both ways right here. All right, so let me start out with axial, right? Okay, so about the Z. So, and I'm going to do it about the origin, right? So it's going to be at the bottom and the center of the coordinate axes. And then the next step is to move it to the center of mass. So about the Z, I'm going to start with my part 1. Right? So I'm going to start with part, and then so 1 right here. Right? And I don't necessarily, I mean, I've done these before, so I kind of know the general way that we're going to arrange the thing, but I haven't made some kind of key decisions yet about like my organization of this, which I probably should. So one good thing to do is mass to start out with, right? Because we already did that right here. And so these are going to be the individual masses, so they might be a little different from here, but this first one will be the same. It's 9,630 kilograms, right? That's fine. Right. But now I'm going to have the radius of all of these are long and slender and have heights and radius. So I'm going to have the radius of each of these things, because I use that in the equations, not the diameter. So I'm going to find the radius of this piece is really 1.83 divided by 2, right there. So, which I probably already have somewhere. 0.915, right? And then I'm also going to need, because this is, I don't actually need this for this particular table, but I'm going to need it for the next one. So I'm actually going to include it, even though it's not 100% necessary. I'm going to have my HI right there, and the HI is 3.66, right? And so now I'm going to have my I, individual I, right? That's going to be about the z-axis, and in this case, let's write that out. Okay, so down the center of the thing, we're going to have 1/2 ma squared, right? Right. So 1/2 9630 a is the radius, 0.915, and so it doesn't extend out too far over to the right. I'm going to write this underneath it, and that needed to be squared. I almost forgot that. So I'm going to square that, and 9630 times and divided by 2. So you're going to get 4,031, right? And if these are going to be kilogram meter squared, right? Now, we won't need this for many of the parts in this, but we might want to have, I'll call it, I don't like calling it DI, but we use it a lot, right? If you look at the parallel axis theorem, where did they bring it up? Yeah, they like to call the distance that you move as d squared, right there, d squared. I know that can be confusing because for diameter, but this is just the d, right? And then the last one, I'm going to take mi di squared. And so the di is going to be 0, and so it's going to be 0 in this one. But this is a placeholder because we're going to have to do this. Now, why is it 0? Because it is on the z-axis, right? We didn't have to move it anywhere. It's right centered. Right, so this will make more sense as we go through and do more of the parts. So part 2 is the cone, and we were told that it has a mass of 1,330 kilograms. And just let me stop for a second and check out. No, that's not mine. Okay, I was looking to see if there's any students coming in via with an email. Okay. Now the radius of each of the cone. Let's see. We have to double check what the moment of inertia thing says to use. Yeah, they use the radius. So we're going to use the cone, and we're going to use for this. It's 3/10 a squared, and they mean, look, here's a little typo. That a, that should be they should have called that a, but they called it right, or they should have used the r right here. So they messed up. It says 3/10 ma squared, even though whatever. So just be aware of that. So we do need the radius of it. So we're going to take the nose. Oh, it's got the same radius, right? 0.915 as above, and the height of it is 1.83. So we're going to have our 3/10 times our 1330 and our radius squared of 0.915 squared. So 0.915 squared 1330, 3 times 10 divided. So we're going to get 334.1. And this is also 0, and this is also 0, because we're spinning it. This is about the z-axis, so we're spinning it about the y-axis. Okay, so now we have, here's where we are going to have to use these two right here. I'm going to go, the best way to do this, I think, is individualized and then multiply by 3. Yeah, I think so. Right, so I'm going to take the masses as 535. The radius is going to be half the diameter here of the rockets. So that's going to be my 0.610 divided by 2. Could almost do that in my head. Yeah, I probably could have 0.305. And then the height of them is given as 1.83. Now, these are going to be about the center, right? So once again, 1/2 m a squared, but there's 3 of them. So I'm going to write this over to the side. 3, and then our 1/2, and 535, and radius 0.305 squared equals. Now note, by the way, we haven't used that h for anything. It's just sort of placeholder, and it took up a lot of real estate right there. But maybe we'll use that in the next one. All right, so they're going to have that squared, and 535 times and 2 divided. But now we're going to take 3 times it. And so we're going to get our 74.65, right? But now, those are all away from the center, right? Those are, each individual one is away from the center. So we've only found what it has to do to spin here, but now we need to bring it this distance, and that distance is the d5 divided by 2, right? So the distance this thing has to move is that. So it's the 3.05 divided by 2. So we get 1.525. Now I didn't leave myself enough room right here, unfortunately. So I wish I had squished it. You know, I could have just made that one really small. I could have left myself enough room here. But I need the mass times, so this individual mass times this squared, but I need it times 3, right? Because there's 3 of them. So I'm going to take 3 times 535 times my 1.525 squared. Does that make sense, right? Because we're going to move all 3 of them away, you know, this is how far away they are from the center of rotation. So I'm going to square my 1.525. I'm going to multiply them by 535, and then I multiply it by 3, right? And so we're going to get 3,733. Now, noteworthy how big that is compared. That's almost as big as that entire big cylinder, and that's all because of how far away they are. Their actual individual rotation about each individual one, not that insignificant, but the fact that they're away from the center really packs a punch. And now these are going to be a little weird. In this, we will actually use probably use this instead of H. I'm going to call it. We're going to treat that as L. You could even say this is or L if you want to. And once again, there's 3 of these, but I'll put the individual masses first. So we got 21.9. The radius of each one is 0.305 divided by 2, right? So that's that divided by 2. So 0.3052, right? So 0.1525. And then the height of each of them, which is really the Li, that's going to be our 0.3. That's very small in my diagram, right? That's just the little height right in there, but I didn't get the drawing all that well. It's really kind of the length. And there's a little bit of an estimate because of the intersection of that isn't exactly, it's not flat. It's got this curvature to the thing. So that's definitely a source of error if you wanted to say. So 0.3, right? Now the I, these are little tiny cylinders. The I is going to be about this one right here, right? So we have 3 of them, right? There's still 3 of them, so we're going to spin these things. Okay. So we're going to write 3 times 1/12. Oh, there's going to be a lot of, this is going to be a big mess right here. Let's see if we get it all. I don't think we can. With the mass of them, 21.9. And now we go 3 times the radius squared, 0.1525 squared, plus, so we're going to have to continue the line down, L squared, which is this, 0.3 squared, right? So that's squared times 3, 0.3 squared, and add it together. Multiply by 21.9, divide it by 12, multiply it by 3. It doesn't have a whole lot, right? It's a pretty small number, and it's really just sort of an error compared to these others, right? It's not going to do a whole lot. But now the distance that this thing has to go out, now we have to do a little bit of thought for this, because it's really going to be, well, we could do it either way. I think I'm going to take the radius of 1 and add 1/2 the length right there, all right? You could go either way. You go to that outside one. So let's take the radius of 1, 0.915 plus 0.3 over 2. All right, so 0.915, 0.32 divided plus, all right? So we get 1.065, and now we're going to have 3 times, so this is going to be the mass, 21.9 times this squared, 1.065 squared. And it's not going to be a lot because they are pretty small. But we're going to square that, 21.9, and multiply it, and then multiply by 3. Boom. And we're with a 74.52, which ain't a lot, but it ain't chump change either. So what we're going to do here And sometimes I'll even put another column in there so you might see. We don't need to add any, well, we need to add this column up, and we need to add that column up. And this video is going to be too long. I could just feel it. But what are you going to do, right? I only give you one homework problem. It's just a really long homework problem. So I'm adding those in our 74.65 and add, and then the 0.8743, which hardly even mattered. So we get 4,441. That's just the individual spinning, but now we also need to have account for the fact that distance is away. So these are really the parallel axis theorem effects of the thing being far away. So we go 3733 and 74.52 and add them. So just 3,808. So if we want to have the moment of inertia, and this is about z right there, and this is not just the moment of inertia about z, but it's also the moment of inertia about z, center of mass, is going to be the 4,441 plus all of these things moving over. So we add them together, and we get 8,248. And these are kilogram meters squared. And let me take a look at my time. I might want to break this up into another video. Yeah, my time's at 26, so I got to go to another video onto the thing. Maybe it'll make it faster. But if you take a look at the answer here, right, so you can see that they're basically the same thing. Moment of inertia taken at the center of mass and aligned with the output coordinate system, or you have moment of inertia taken about the output coordinate system. Either way, this is 8,238, and we got 8,248. So we're darn close. It's probably all just round off error, but also remember that the mass was slightly different. All right, so I'm going to conclude the video here, and we will see another one coming out. Maybe the concluding, I think this would be the concluding video for this.